This presentation is delivered by the Stanford Center for Professional Development.
Any questions about anything before we delve into our next great topic? All right, you're feeling okay. Good. So a lot of today's class is actually about life after this class, because we're getting pretty close to the end of this class. And so one of the things I want you to just kind of know about, so you can think about it, are what are some of the options that are available to you afterwards, whether or not you're just thinking about declaring a major, or if you've already declared a major, or you just want to get sort of a lay of the land of what's this whole computer science thing all about. Because probably the biggest thing I would stress, despite the fact that you just spent the last 9 weeks programming, is computer science is not computer programming. Okay? A lot of times the two get equated, but if it was called computer programming, this class wouldn't be called programming methodology. We'd just call it something like programs that work, right? And we wouldn't worry about style and all this other stuff and good software engineering principles. And at the same time, computer science wouldn't be called computer science. It would be called something like programming, right? It's like, oh, what did you major in? Oh, I majored in programming. And that's like, you know, that's when you say, oh, I'm sorry, I think you can get shots for that kind of thing now. Because it's not just about programming. There is programming in computer science, but there's actually a science to the field, and there's a lot of things that go on outside of programming, and that's what's important to, in some sense, appreciate. So if we think about life after this class, let's first kind of deal with some of the short-term logistical kind of things. Like, you just took this class, you might think, well, there's a couple things you probably think. You think, hey, Maron, that was kind of interesting. I might consider taking 106B. You might consider, hey, Maron, that was interesting. I might actually consider minoring or majoring in computer science. And you might say, hey, Maron, that was interesting in the same way, for example, that dropping a brick on my head is interesting, and I'm going to run screaming. And if you're thinking the third option, I apologize, because that was not the point of this class. But here's a few things that you can potentially think about, even if you're in the third option, and definitely some things to think about for the first two options. And I guess there was always that option of the, oh, I got the general education requirements out of the way, and now I will go on figuring out what to do with the rest of my life. And if that's the case, you should pay attention as well. So what happens after 106A? So here's CS 106A. This is where we're all sort of happy, and we're scrappy, and we're, you know, making social networks. And life after this, kind of, you know, your next immediate step is actually pretty clear. There is a class, CS 106B, that's called Programming Abstractions, which is the next class to take. And this is, yeah, that was pretty exciting. And that class is all in a language called C++, so you'll learn a whole new language. Although you'll realize when you actually see C++ that a whole bunch of things in it are just the same as Java. Like for loops, while loops, all that stuff, exactly the same. Whole notions of parameter passing and methods and decomposition and objects, all those same things exist in here. Okay? But what you also will get with this is a class called Programming Abstractions, because so far what we've done is used a lot of abstractions. Like we had a notion of, for example, an array list or a hash map, and you sort of just got a hash map and you used it and you were like, oh, that's kind of cool, I can put stuff in, I can take stuff out. And in this class you actually think about things like, how do you implement a hash map? Right? Someone somewhere had to actually write the code for that thing, or for an array list, or for the graphics that you use. How do you actually write some of that stuff? And there you get into a whole bunch of trade-offs with how you can make things run more quickly versus perhaps using more memory versus different kinds of programming techniques that actually come up. There's also some really cool ideas that come up in here, which are just sort of mind-blowing ideas, which is a notion, for example, one of them is called recursion. Which is, you know, so far we have methods, and methods call other methods, and they call other methods. What if a method called itself? Like, that's kind of weird, Maron. Like, why would a method call itself? Because some functions are defined in terms of themselves, right? If you kind of think about the factorial function, anyone remember this function? The n function, right? This is n factorial, and all this really is, sorry if I just shattered your eardrums, is n times n minus 1 times n minus 2 times times 1. You just multiply everything together. The friends of mine who are mathematicians say, but Maron, you know, I grow tired, I grow weary of all this writing. The way I actually define this function is n factorial is equal to n times n minus 1 factorial. And you look at this and you're like, but you're defining the function over here and you're using the definition of the function to define it? That's what recursion's all about. You can define a function in terms of itself. And it turns out, yeah, factorial, That's kind of a simple way to understand it. It turns out that this is a hugely powerful concept that allows you to do all kinds of things. And this is kind of another cool thing you get in CS 106B. Okay? Now, you might say, okay, Maron, that's still sounding like programming to me. Even though I'm learning these cool concepts, isn't that just, isn't that a programming class? And in some sense, yeah, this is a programming class. There's other options that are also available to you now that kind of fall into the category of being part of the CS major or the CS minor. A set of classes called CS 103. And CS 103 come in a couple different flavors, like vanilla, grape, and pork. No, they come in, there's an A-B sequence. And there's an X. Yeah, I can't think of anything in the world that would come in those three flavors. But if you can find, there's some pretty funky ice creams out there. I guess that, but I've never seen pork ice cream. If you see it, let me know. And I'm a big fan of ice cream, but that's a whole separate. It's like, and now we will talk about ice cream. No, something completely different. So it comes in these two flavors, and this is really a class that in some sense is about discrete math. And you might say, oh, gee, Maron, besides your class, I'm taking calculus, and that's about as much fun as like sliding down a 50-foot razor blade. Why would I want to do that again? Not on the sharp side, right? Just imagine the other side of the flat side of the razor blade, and it's been like, made slick, and it's like a big slide. It's fun. Wait until, my friends in the math department see that. Anyway, why would I care about this discrete math thing? Well, first of all, this is an operative word here, which means this little symbol that you may have grown to know and love, our friend, the integral, just not around, right? This is all discrete. This is like, hey, you know what? What we want to think about are some things that are useful to us in a computer science context. And computers, at the end of the day, are digital objects, right? They have ones and zeros, which means there's a whole bunch of things like sets, for example, and logic that come up in these things. But there's also interesting ideas that come up in here like computability. And you're like, what does computability mean, Maron? That means, interestingly enough, there's actually some functions that can't be computed. And you can prove that they can't be computed. And you're like, oh, that's kind of interesting. Yeah, and you can find out what those are. As a matter of fact, in these classes, which at this point you're now ready to take either A or X, and the prerequisite for, or the co-requisite for taking 103B is 106B. So after 106A, you can either take 106B and 103A is now also opened up to you as well. In these classes, you get exposed to some things like some of the biggest open problems in computer science. Now, there isn't time to go into what some of the biggest open problems in computer science are, but there's a problem called the P equals NP problem, right? And this is a big question mark. Basically, we just don't know if these two things, one of them named N, not N, P, and the other one named NP are equal to each other or not. And you'll find out what those are in the class, and you might say, okay, Maron, why do I care about that? Because it turns out this little problem here has a $1 million prize associated with it. And it's simple enough to explain that after having had 106A, when you take these next two classes, you'll actually get exposed to this problem. It's one of those things that's like, a minute to understand, a lifetime to master. And no one's mastered it yet. But in some sense, this is also a problem that's only about 35 years old, maybe just slightly over than 35 years old. So it's not like this problem that's existed for like, hundreds of thousands of years and, cave people were writing, does P equal NP on stone tablets. This problem actually came, sort of to the fore, and people realized it was an important problem in the 70s, which means it's possible that it'll be solved in your lifetime. And it's possible that you may be the one, presumably, solving it in your lifetime, because it would be difficult to solve it if it wasn't in your lifetime. Okay? But these are the kinds of things you could actually get exposed to relatively early. You're like, well, why is he saying that? It's just because I can. Okay? And along with these other, like we talked about, that whole thing with like graphs and social networks and 6 degrees of separation. Yeah, guess what? That's all part of discrete math. That's just some mathematical structure that we can actually analyze, like how far apart things are in a graph, or how we actually model a social network explicitly, or for example, a computer network. Turns out computer networks, if you ever wonder, hey, why can't I connect to this web server somewhere? Well, there's a lot of reasons for that, and part of them may be that there's some problem with the network somewhere, and understanding how robust your network is something that you could actually think about in terms of graphs. Okay? And there's a bunch of other things that come up here besides computability and discrete structures and those kinds of things. But these, to give you a little historical point, were my favorite class at Stanford. So when I was a wee tyke, these actually weren't numbered 103, they were numbered 109. But they were my very favorite classes. And I took the 106s, I took 106A and B, and I loved them. I thought, oh, they're great, I love all this programming stuff. And then I got here, and it was like the clouds parted. And I was like, this is the coolest thing ever. And then I spent the rest of my life doing it, and I'm still doing it. So You know, even if programming by itself doesn't necessarily turn you on, but you think, you know, programming's interesting, is there also some deeper science or some mathematics? Because for a lot of people, you know, they didn't necessarily get exposed to computer science earlier on, but they did get exposed to mathematics. This might be the kind of thing that really turns you on. Now you might say, okay, Maron, math doesn't necessarily turn me on, programming turns me on. Besides that 106 class, what other options are there? There's two other classes, CS 107 and 108. And these classes basically look at building, in some sense, larger scale systems. So this involves object-oriented systems, and in some sense, building larger applications. So you build some things here which are outside, you know, the scope of a 1 or 2 week project. Like you might spend like 4 weeks on a large project in this class by the end and actually build a, you know, fairly substantial application. And 107 looks at a whole bunch of issues that in some sense we like to think of as lower level kinds of issues, but involves a lot of programming, and it gets into sort of the nuts and bolts as to how does the software sit on top of the hardware of your machine, and how do these things kind of interact, and getting into understanding memory better and a whole bunch of other things. And if you think about this set of classes like 106AB, 103AB, and 107, 108, if you were to take that set of classes and add to it 2 CS electives, that's the minor. Okay? So the minor is basically just these 6 core classes. You need to take math up to math 51, I should say, as a little side note, just in case you're wondering. That's just something that, you know, we're not responsible for that. It's just kind of required. And then 2 CS electives beyond this kind of stuff, and then you're getting a minor. Okay? So if you want to kick it up a notch beyond a minor and think about the major, actually I'll just leave this up here. 2 CS electives, you sort of add that all together and it equals the CS minor, which is kind of fun. Okay? Now, if you want to think about, besides just the CS minor, potentially actually majoring in CS, you might want to think about, okay, first of all, what are some other things that I can do in computer science beyond the introductory classes? And there's a whole bunch of things. There's something that we call artificial intelligence, or just AI for short. And there's a whole bunch of aspects of artificial intelligence. At sort of the highest level, it's the notion of trying to make your computer work more intelligently, in some sense appear to be more intelligent, sort of on the order of the intelligence of a person. But really this has a whole bunch of subfields to it. For example, robotics and various other kinds of things like computational biology. There's a lot of computational biology that's grounded in artificial intelligence. Data analysis. And I'll show you some examples of these as we go along. You might say data analysis, Maron, that doesn't sound very exciting at all. Well, let me give you a simple example of data analysis. Anyone know what that is? Like, it's a squiggle on the chalkboard. Yeah, that's the stock market, right? And you have, yeah, as a chalk squiggle. Really, it's the NASDAQ Composite Index. Look it up. It's a remarkably close rendition. And this is today, and there's a whole bunch of people in the world who are wondering what happens tomorrow. And if you can do slightly better than 50% predicting what happens tomorrow based on analyzing all the data from today and before, you make tons of money. Okay? And if you wonder, like, is this really the case? Yeah, in fact, anyone heard of a company called D.E. Shaw? Anyone? A few folks? Yeah, it's David Shaw. He was actually a grad student at Stanford in computer science. And this whole, you know, I wouldn't say he started this whole thing. This actually existed long before that. But there's whole companies whose entire business is based on the notion of quantitative analysis. And guess who are a bunch of people that they employ? Computer scientists who go and do the data analysis and actually figure this out. Okay? So the application and understanding what are all the variables you care about and the information that actually exists in the stock market that you can extract and model with different kinds of algorithms to make your prediction is all part of what computer science is all about. Okay? So a few other things in here. Besides AI, there's various other kinds of little areas. And I'll show you some more pictures, like robotics. Anyone heard of the DARPA Grand Challenger, a little robot called Junior or Stanley? Yeah, oh, Junior, he's so cute. Let me show you a picture. Because this is a robot that in some sense is a car, right? And there's no reason why a car can't be a robot. Just think of if Carol had wheels on it, and instead of move, you had move at 60 miles an hour. You'd be doing the same thing, except you'd be doing it in a simulation. So here's then, you can see the little S on there. This is, you know, Stanford's car Junior. And this is a car that's basically a robot. It doesn't have a human driver, at least most of the time. right? It has things like various kinds of sensors on it, like various sorts of radar and other kinds of laser range finding that sense what's going on in the world, and then it makes decisions. Okay? And so let me show you a little example of that. So here's a little video. That's not what I wanted. I wanted this. Here's a little video of Junior actually involved. Yeah. The joys of software. That's another thing you can do as a computer scientist. You can fix other people's bugs. All right, or you can pretend that let's look at a different one. Here's what's actually going inside Junior when it's actually running along. It's sensing a bunch of things about its environment, and you can actually see, like, it's driving along. This is where it has some uncertainty or some distribution over where it thinks it is, where it thinks different lane markers in the road are. And it's doing all this by actually taking pictures of the road, analyzing them in real time, and then making various kinds of decisions about where to steer and where to go. Right? And this is all happening in real time. Right? This isn't like, oh, we had to load all this data and figure it out on some supercomputer. There's just a little bank of computers inside of Junior that are actually figuring this out as it goes along. Right? It figures out certain places to stop or how it's going to remaneuver itself. Let me show you the set of computers that are actually doing this. Right? They're just sitting in the back of the computer. So yeah, there's a few different machines in here, but it's sort of computational power on par with what you're going to have in your dorm room by the time you graduate, basically. So it's not like something outrageous where it's hundreds of millions of dollars of computation. It's a bunch of PCs that are wired together. Okay? Here it is cruising up to a stop sign. There's a car going the other way, and it's just going to come up to where it needs to be, and it's done. All right? Let me show you one more quick example of Junior actually parking. Okay? So, nope, not what I want. The joys. All right. So these little red marks over here are actually cars, and it's basically sensing that these areas are blocked, and what it wants to do is get to a parking spot that's between two cars right here. So it plans this little path, and it looks like it's going to rear end this other car over here, but really all it's doing is repositioning itself so it can replan to be able to back up and then pull into the parking spot. Right? And if you think about all of the dynamics that need to be going on to do this, all the low-level stuff to sense where things are, the high-level planning to figure out how sharp of a turn it can make, and now it's going to back out and drive off. All of this stuff is basically just software. It's a computer science problem. And that's how the Junior team actually views this robotic car. They don't view it as a big mechanical engineering problem. They view it as there's a bunch of sensors in the car, and there are some actuators, like they can hook up computers to the steering wheel to turn it. And really, the whole problem is solved in software. How to do the planning, when to turn the steering wheel by how much, when to figure out if lanes are blocked, stuff like that. Okay? So that's a little bit of AI. Let me show you a few other fields. Okay? So besides AI, and there's a class related to this, CS 121 or 221, you sort of have your choice. This is kind of a survey of artificial intelligence, and this is kind of, in some sense, modern techniques for artificial intelligence. So if you really want to go and build robots, I'd sort of suggest you take 221. If you want to get a lay of the land of what's in artificial intelligence, you can take CS 121. Okay? Some other things that you take along the way are a class like CS 140, operating systems. Right? And if you've ever wondered about things like, hey, I have my Mac. How does my Mac actually do all this stuff for me? How does it take care of a file system for me? How does it take care of the fact that there's multiple things running at the same time? How does it deal with the fact that I may actually be running more applications than I actually have real RAM in my computer? There's a notion of virtual memory, for example, where it uses your disk for part of memory. That's all stuff that's covered in an operating systems class. And if you're interested in systemsy kinds of things, there are just a ton of things you'll learn in here that you can kind of build on, right? You want to go build your own operating system, right? 20 years ago, that was an unheard of kind of thing. There was a couple big players, and they were like, oh, well, we're building the only operating systems in town. And then this guy named Linus Torvalds came along and just said, hey, it's not that bad. And he created something called Linux. And now millions of people actually use Linux, and it just uses a bunch of these standard operating systems principles. Okay? There's some other classes. I won't give you all of them, but there's kind of a class on data structures. So we talked a little bit about data structures in this class a bit when we talked about putting a bunch of things together to kind of create a bigger data structure and keep track of information. But CS161, there's actually, if you imagine in the sense of how many cool data structures might be out there that do all kinds of funky specialized things for you, there's a ton of them, and you'll learn a bunch about a bunch of them in CS161. And there's other classes that are electives in the department. But rather than going through all the classes, let me just show you some of the areas. Graphics. Okay? Graphics is a big area that's in CS. And it turns out, interestingly enough, of our graphics faculty, Pat Hanrahan is one of the faculty here. He actually has not one, but 2 Academy Awards. Right? Interestingly enough, he's actually got Oscars, right? So this is the kind of thing, and you might wonder, why does he have Oscars, Marin? Well, because guess what? There's all these animated movies these days. There's a system called RenderMan that was actually responsible for being able to do a lot of the rendering for original computer graphic movies. He was on the team that built that system. And he's done a bunch of other stuff since then, which is why they gave him a second one in 2004, okay? There's a guy named Ron Fedke, and I'll show you a little animation that his group developed. So here is what looks like a lighthouse and water. And here's basically a realistic computer animated waveform crashing over the lighthouse. Right? This is all done. This wasn't like scanned over some real lighthouse when there was flooding. This is all basically done as a computer simulation. Right? That's the kind of stuff his group does. And a matter of fact, for doing stuff like this, it doesn't just show up in little animations to show in 106A. If you happen to see like Star Wars 3, he was in the credits for it. If you happen to see, what were some of the other movies he was in? Anyone see Terminator 3? Horrible movie, don't see it. But he was in the screen credits for that as well. Evan Almighty, yeah. So there's serious movies that involve major computer graphics where the stuff that's being done here is actually at the cutting edge of that to be able to figure out new ways of actually doing things with computer graphics and actually doing the animation. Okay? There's also something else sort of related to this. So there's kind of movie graphics. There's a bunch of other graphics. There's also a lot of stuff actually dealing with digital photography. So I'll show you a little example of that. Wouldn't it be cool if you could take one picture and just refocus it anywhere? So there's a group that does that here by building something called the light field camera. Here are the folks that are involved. Pat Hanrahan is one of them. And here's just a little animation of if you have a light field exposure, okay, one picture you can just refocus. Kind of cool. But there's other kinds of things you can do. Like here's a misfocused camera. You just bring the picture into focus automatically. Yeah, here's a really blurry one. Ah, pretty hardcore. And here's focusing through a splash of water, right? So it doesn't just have to be a picture of some solid object. I hope you can actually see that refocusing while it's happening. Here are some crayons with some color. This is kind of fun. Then we get into the audio part. I won't show you the audio part. It's kind of more of the same. But that's kind of the basic idea. They're actually starting a company around this idea of light field photography, where you have a camera, and just the way the lens is constructed and the amount of light that you sample at various kinds of not wavelengths, but at various depths of fields, allows you to take this image and then be able to refocus on different parts of it later or clean things up or whatever. Okay, that's just another thing that's kind of based on graphics that you wouldn't necessarily think of, right? But photography really is taking some sample of the world, turning it into a graphical image, and then doing manipulations on that image. So a lot of the things that happen in graphics apply directly to photography as well. Okay? So besides graphics and robotics, we talked a little bit about those. There's folks that worry about stuff like databases, like handling large volumes of data and streaming data and different kinds of things you could do with data. And I was kind of thinking about this, and I was like, what's a demo that I could show having to do with large volumes of data? Because that's not something you can actually draw a picture of real easily. And then I just thought I'd show you this. Okay? Because Google came out of Stanford. It came out of a group of folks who did things like understanding data structures and the algorithms associated with them, and who understood how to keep track of large volumes of data and be able to do manipulations on that kind of data. And as a matter of fact, in the early days, most people don't know this now, but if you went to Stanford, or I shouldn't say stanford.google, it was google.stanford.edu was the web address for Google. Okay? And it turned out that at some point this was actually eating up so much of the entire bandwidth on campus that some folks said, you know, oh, you really need to like go and move this somewhere else. And then they actually created the company Google, which is based on a misspelling, right? The actual, you know, anyone know what an actual Google is, which is the correct spelling of Google, is 10 to the 100th power. It's 10 with 100 zeros after it. And so Larry Page and Sergey Brin were grad students here, and they wanted to think of some name that captured the largeness of Google or of the web search that they were doing. So they went off and registered Google because that's how they thought it was spelled, or at least one of them, and I won't tell you which one thought that. When they were grad students, right? And then when the other one of them came back to the room and looked at it, he said, you misspelled it. But two things transpired. One was that this .com was already taken. And the second one was when you're a grad student, and at the time it was like, you know, $50 or $70 to actually register the name, that's kind of spendy when you're like living on ramen. So that's what it was. Okay? But it just shows you the kinds of things that get done by taking basic ideas in computer science and building them to a larger scale. Now there's a lot of other things that also go on. I'll just give you brief sampling. Cryptography, which is big for web security, right? It turns out a lot of the web is actually pretty insecure, much less secure than you would actually imagine. Anyone ever had a credit card number stolen? Few folks, yeah. When you get your credit card number stolen, then you think twice about a lot of the transactions that you make. I had it happen actually a couple times, and I still like, you know, Christmas time rolls around, I'm just like online shopping till the cows come home. But it's important to actually think about what's secure and what's not secure, and there's actually a group that deals with cryptography, especially security, in the context of the web. Other kinds of things that go on. We talked a little bit about AI, kind of a subfield of AI, which is growing into a whole area of its own, is machine learning. And I talked a little bit about things like biology or predictive data analysis. There's also actually machine learning affects your life on a daily basis, whether or not you know it. How many people have a spam filter on their email? Anyone? Yeah, did you know that chances are, probably in all likelihood, your spam filter is actually based on machine learning. It's seen a whole bunch of email, some mail that was spam, some mail that wasn't spam, and it learned. No one told it what was spam and what wasn't spam. It learned to figure out how to distinguish between what's spam and what's not spam. Now, it's not perfect, right? People aren't perfect either, so sometimes you get messages in your inbox that are spam, and every once in a while, rarely, but it happens, someone sends you a message and you never hear about it, and they're like, hey, I sent you this email, and then you go check your spam folder and it shows up in there. But spam filtering is another one of these things that in the last 10 years or so is something we take for granted and don't think about the fact that there's actually a bunch of science underneath the hood as to how to do this, and people continue to do research how to improve it. There's a bunch of other things based on this, like robot navigation. Some of the stuff you just saw with Junior is actually based on learning landmarks of the road or learning where lanes are on the road or what obstacles actually are. There's a ton of other things. I'm just giving you a sampling. A field we called HCI, which is human-computer interaction. And a lot of this is things like interfaces, like how do people interact with a computer, or based on the sorts of visual things that are available to them when they interact with a computer, what kinds of actions do they actually take? To what extent do people humanize computers? That's kind of the most interesting thing, right, is that if you actually have some application that's running, at which point you think it's just doing the right thing for you, people, especially people who aren't, you know, the most computer-savvy people in the world, actually begin to ascribe human qualities to machines. And sometimes that's not a bad thing, but understanding what those interactions are and the social phenomena as well as the actual science in terms of the computer behind it is what gets studied in human-computer interaction. Now, if any of this has interested you at all, there's a guy you need to go see. One guy you could go see is me, and I'd be happy to talk to you about any of this. But there's another guy you can go see whose name is Dave Kozlow. And Dave is what we refer to as the CS course advisor. I'll just put the CS advisor up here. He's in Gates 160. He's the guy you see when you want to declare computer science. Not that I'd be putting in a plug, but he's an interesting guy to talk to about some of the different possibilities in the field. But open invitation, right? So this class is going to end like after Wednesday or after the end of the week or after take the final, depending on how you look at it. Don't be a stranger. Right? Come on by. If you want to talk computer science, if you want to talk about what's possible to do in the field, come by. My office hours will be on the web, or send me an email to set up a time to talk, and I'd be more than happy to take you through a bunch of this stuff. So besides Dave, there's me. Now, last but not least, and I shouldn't say last but not least, you might say, Marin, computer science is kind of interesting, but are there other related majors that I should consider? So in the sense of full disclosure and fair play, there's computer science. There are some other possibilities, like there's electrical engineering if you're more interested in the hardware side of things. There's math and computational science. And math and computational science is more of, if you're interested in the mathematical side of computing, you'll still get a lot of math if you do computer science major, but if you sort of are really kind of immersed on the mathematical side, math computational science is something to consider. And there's also a major called symbolic systems, or just SimSys. And SimSys is also a fun major. It's actually a combination of linguistics, computer science, philosophy, and psychology. I always forget the last one, except it's always different every time which one I forget. And the basic idea here is to think of both humans and machines as symbol processors, right? People are symbol processors in some sense because they take in symbols of the world, namely language or visual iconography that they actually see, and they make some sense of it, and then they act in the world. And you could say, hey, computers are the same thing, right? They're just taking in a bunch of symbols like information that's in a file or something they sense about the environment through some sensor, and they take some action. Like Junior, right? He looks around at the environment, and he sees the distances of various objects, and he takes some action, which is namely driving this robotic car, right? And if you think of those things as equivalent, right, one of them being made out of protein and the other one being made out of silicon, you begin to draw a lot of interesting analogies between the two. Okay, so symbolic systems is another kind of interesting multidisciplinary major. But now you might say, okay, that's interesting. You've told me about all these fields, but you told me the computer science was more than just programming. And so far, it's unclear what I might be doing other than programming all these cool applications you're showing me. So let me tell you about a few of them. This is what I refer to as kind of the peanut butter cup version of computer science, which is you can take computer science and a whole bunch of other things and mix them together, and they're just two great tastes that taste great together. And I'll show you a lot of examples of that. So there's CS and business. Okay? If you're interested in sort of the business sides of things, product management is a whole field or a whole area that people go into, especially in high-tech product management, which are people who don't necessarily program, but they have technical backgrounds to be able to define what products are going to do and how people are going to interact with them. And so if you look at a lot of high-tech companies, people who are product managers who are taking more of a managerial role and defining role for products, many of them, in some sense I'd actually say most of them, probably have a technical background. In a lot of cases it's computer science, even though they do no programming. Okay? They do product definition. Beyond that, and this is kind of a popular one around here, entrepreneurship. Yeah, that's good enough. I always get nervous writing that. And that's the whole notion of you think about people doing startup companies, right? There's been a ton of startup companies. I can't name them all because actually over the last few years there's been over 2,500 companies that have come out of Stanford. Some of them are big and you know about, like Google and Yahoo and Cisco and Sun and HP and all these other ones. And there's a whole bunch of smaller ones out there that also did pretty well. Anyone ever remember Evite? Anyone ever send an Evite? You're like, yeah, I'm having a party. I'm going to Evite my friends to it. Yeah, that was started by a guy I lived next door to many years ago. And they did pretty well. They got acquired eventually, but life was all good. And the whole notion here of thinking about startup companies. Now, one thing that's interesting is a lot of people think, oh, well, if I want to do entrepreneurship, I should go do business, right? Well, what I'd actually challenge you to do if you think that is go find out about the backgrounds of people who are things like successful venture capitalists and see what they did when they started. And one of the things that you'll actually find, which is surprising, is most of these people didn't start as business people. They started as technical people who actually went and did interesting technical work and at a certain point realized there was a need and then moved on into the business realm. Okay? Tons of examples of that. I'll just give you a quick one. Eric Schmidt, who happens to be the CEO of Google, PhD in computer science, right? Not an MBA. So entrepreneurship, that's not to say an MBA is a bad route. It's just to say that realistically, if you look at what a lot of people have done, the route to actually getting there in many cases actually flows through a technical area. Okay? There is also finance in the sense of computational finance. Right? Again, not only in predicting the stock market, but there's a whole bunch of people that what they do is they worry about different kinds of modeling algorithms or managing different kinds of funds, basically by thinking of financial markets as a computational problem that they model with different kinds of data structures and different sorts of algorithms to potentially make predictions on or just to get insight into. Okay? If you're interested in this kind of stuff, there's actually a program called the Mayfield Fellows Program. If you do a search for Mayfield Fellows Stanford in your favorite search engine, you can find out more about it, which is actually a program that sort of, you learn about entrepreneurship. You go into an internship with a startup company to learn more about it, but you actually get immersed in thinking about the different issues of starting a company. There's CS. We'll just leave the CS up here. And biology. This has become a hugely popular area these days. Okay? And so there's a whole bunch of things like bioinformatics. In bioinformatics, there's kind of different flavors of CS in biology. Is thinking about the information systems that keep track of biological data or that keep track of medical data, right? So if you think about if there's a whole bunch of medical data that's being kept on you, like your medical records and results for tests and a whole bunch of things that I want to be able to slice and dice in different ways or understand how, for example, symptoms that you have might be related to some other symptoms or some other diagnosis that happened in the past, these are the kind of information systems that deal with that. And we have a whole program here called the BMI program, Biomedical Informatics, that just deals with that. But beyond that, there's also fun things like genomics and proteomics and doing things like being able to look at gene expression data and DNA and be able to determine what kind of diseases do you hereditarily have more of a disposition to because of your genetic makeup. And if you're interested in this kind of stuff, there's actually a program also in bioengineering. They don't right now have an undergraduate program. They have a graduate program. They're going to form an undergraduate program that's something you could be interested in. Or it's something we actually have sort of a sub-areas of the computer science major that you can also do this kind of stuff in. CS and law. Another big area, right? I don't need to list them all out, but you can imagine intellectual property, copyright, patents, all kinds of digital media, file sharing, right? Just a huge area that goes on here. Now, one thing that's kind of interesting that also sometimes surprises people is they say, oh, I want to be a patent lawyer. I want to go and deal with all these issues like making sure that file copying like of music is legal for everyone. So I'm going to go and be a political science major because that's what I should do to go to law school, right? Turns out if you actually want to be an intellectual property lawyer, you need to have a technical background. There's a list of approved areas that you could have done for your undergraduate degree that allow you to become an intellectual property or copyright lawyer. Computer science recently got added, well, I shouldn't say recently, got added to that list about 15 years ago. Political science, not on that list. Okay? So something you should probably know now, if this is the area you're thinking about going to, you need to understand the technology to understand how intellectual property and copyright issues apply. You need to understand what an algorithm is, what parts of an algorithm are obvious versus what parts of an algorithm are not obvious. That's what allows people to do this work. Okay? And then last but not least, CS plus, well, CS. Right? So you can just you don't have to mix computer science with something else. You can just do computer science. And obviously, programming is part of this. There's a lot of people who are very happy being software engineers, and there's lots of jobs in software engineering, and life is good. But there's also people who go into, for example, engineering management. Most managers in computer science are not professional managers. They are people who at one time were programmers or engineers and worked their way up through the ranks and eventually became managers and became senior managers and became VPs and the whole deal. Right? So it started by having a technical background. It didn't start by saying, hey, I want to be a manager and having someone hire you to be a manager. Okay? And there's also, and this is near and dear to my heart, so I'm just going to sort of wrap up quickly, teaching. Right? So you could think about computer science as a field that you go into because you want to teach it to other people, in addition to perhaps doing some stuff in it yourself because you find it interesting. But if teaching at all is something that's interesting to you, or like when you were in your section, you were like, hey, section leading is kind of cool. This is something I might consider. There's the CS 198 program. And this is a program I've talked about in the past, but I want to just spend a little bit more time talking about. And what you need to go into CS 198 is you need CS 106A and B. Or you could have taken X, but at this point it's kind of too late to take X. So what you really need is CS 106B. After one more class, you're eligible to become a section leader. And being a section leader, you might say, oh, well, what does that involve? And it turns out to involve a whole bunch of things. One is that you actually teach a section, which is kind of cool in itself. Because you get to learn the material a whole lot better when you teach it to someone else. So I realize that now. Like every time I teach a class, even if it's a class I've taught 10 times before, the 11th time you do it, there's some new little nuance about something that you learned somewhere. So you learn the material that much better by teaching the section. You also get to know other section leaders. So there's kind of a social aspect to it, and especially if you want to go into computer science, this is a great way to meet project partners and other people who you know are really interested in computer science and motivated. You also get to meet faculty. So when it comes time for getting letters of recommendation, which is something that people don't necessarily think about early on in their program, but then later on, how many people are thinking about letters of recommendation now? Like it's getting to that grad school application time? Yeah, and how many people wish you had thought about it earlier? Yeah, mostly the same hands. This is a good way to do that, is to actually get to know people who are involved in teaching. And we have regular staff meetings, and it's a good way to sort of think about that. And at the same time, and one last side point I would put in, is that there's a huge network of people who went through this program who are out there. Right, in the sense that if I go to a whole bunch of different companies and look around, especially, Stanford there's a lot of people who go into Silicon Valley and other high-tech companies in very sort of high-profile positions. A lot of them actually came through this program, and they understand that the people who go through this program are in some sense a really great commodity because they have had a lot of experience teaching, so they know how to communicate with people. They have strong technical skills because they had to be strong enough to actually teach this stuff, and they have ties with other people. And so the CS198 program is actually a program that's not just known at Stanford, but it's actually known nationally. Like if I go to other companies or something like that, there's people, for example, they come to visit from like Microsoft, and they're like, yeah, tell me where the 198 meeting is and what's going on there. And they come and recruit from that group of people. And this happens for a whole bunch of companies across the board. So with that kind of said, hopefully this has given you a little bit of a taste for what computer science can be about. Not just thinking about programming per se, which is what we've done a lot of in this class, but programming is really just the first step that opens up a whole bunch of other venues. And hopefully you got a sense of some of the other classes you can take that will broaden your horizons even more, and some of the different areas you can go into potentially with a computer science or related major that can open up all of these possibilities. So any questions about any of that? You're all set? Alrighty, then I will see you on Wednesday.